Combined gas laws. Combined gas law calculations we've looked at in the last couple of lessons. We looked at Boyle's law, Charles's law, and Gay-Lussac's law. And pretty much, after pretty much watching or listening to those two lessons, you can almost see the correlation between all three of their laws and how we can combine them to come up with what we call the combined gas laws. So let's recap a few things. Average pressure of the atmosphere at sea level is taken at standard pressure. Now, we know that that pressure, we use the following sets of units. So 760 millimeters of mercury, 760 torr, which is equal to 1 atmosphere, which is equal to 101.3 kilopascals. Okay, so this is the standard pressure at sea level. The freezing point of water, which is at 0 degrees Celsius, and we were introduced to the Kelvin scale, is 273 Kelvin. Okay, and it's defined as standard temperature at sea level. Okay, so 0 degrees Celsius. Together, these conditions are referred to as the standard temperature and pressure, and we refer to them as STP. So please keep that in mind, because you may be asked to reference to, with regards to STP, which means your standard pressure at 101.3 kilopascals, or 1 atmosphere, or 760 torr. Right? And we're referring to the temperature at 0 degrees Celsius. Normal conditions under which we live are referred to as the standard ambient temperature and pressure, referred to as SATP. Okay, so that's the short form. And when we refer to the ambient temperature, we're referring to it at 25 degrees Celsius, and we're referring to pressure as 100 kilopascals. Also keep note that when we do have temperature in degrees Celsius, we can convert to Kelvin by adding 273. And at 25 degrees Celsius, what is the, at the Kelvin scale, what Kelvin do we have? What is it? You guess what? 298 Kelvin. Okay. Now, looking back at some of the gas laws, Boyle established that pressure and volume are inversely proportional. Right? We know inversely means if one goes up, the other is going to go down. Right? So, if pressure is going to go up, volume is going to go down. If pressure is going to go the other way, then the opposite kind of occurs, right? So, we use the following. Now, Charles found that volume and temperature were directly proportional. Now, another thing to make note of with Boyle's law, we looked at pressure and volume. What remained constant? What didn't change? Exactly, temperature. Okay, so we know temperature when dealing with Boyle's law. Charles found that volume and temperature are directly proportional. So if they were directly proportional in that, if one went up, so did the other. Inversely, one went up, the other went down. And Gay-Lussac discovered that the pressure has the same relationship to temperature as volume does. Right? So here we're looking at pretty much now, we're still comparing all three of them, right? Pressure, volume, temperature. But we also had similar relationship here with temperature and pressure, where if we increase one, then the other one was also going to increase as well. So let's look at the equations that we found. According to Boyle's law, so Boyle's law, we're looking at pressure and volume. Initial pressure and volume equals final pressure and volume multiplied together. Charles found the following. VI over TI equals VF over TF. And Gay-Lussac looked at pressure and temperature, as follows. So if you look at all the letters that we've used, you can almost think that, well, why can't we just combine all of them? Okay, and that's where we get the idea of the combined gas laws, where we're combining Boyle, Charles, and Gay-lussac. So the combined gas law. Boyle's law can be used to solve for changes in volume when pressure changes. So the gas must be in a closed system and the temperature must remain constant. Right? Remember that for each set of laws, there was always one constant. Charles' law can be used to solve for changes in volume with temperature changes. Only works in a closed system in which the pressure remains constant. So all these, remember, keep in mind that they all have that consistent, that there's that one constant, right? In Charles' law, pressure. In Boyle's law, it was temperature. Right? Remember that we also, whenever we're dealing with temperature, we're always using or referring to the Kelvin scale. And with Gay-Lussac's law, can solve problems in which the amount and volume of gas remains constant while the temperature and pressure change. Okay, so we're looking at all as closed systems. So here we have Boyle's law, where volume is inversely. Right? So if it's inversely, V, okay, with the inversely proportionate, or the proportionality symbol, and it's 1 over P, as opposed to V is proportional to T, right? Because it's not an inverse, right? So which means that if volume went up, pressure went down because it's an inverse. Okay. Now, combining these two expressions gives us the following. We've got V, as we said, is inversely proportional to 1 over P. Now we're going to add in that times T. Right? So what we're doing is we're combining, right? We've got V is proportional to some kind of factor that deals with these gases. And so in the first one, according to Boyle's law, it's 1 over P. The second one, in Charles' law, it's proportional to T. So why not combine them as follows? Right? And so we get the following. V is proportional to T over P. And how did we get that? Well, look at this. Right? Whenever we're multiplying a fraction by a whole number, you always multiply the numerator with the whole number. And you simplify it as V is proportional to T over P, which means we increase volume, temperature will increase, but pressure will decrease. Okay, we're looking at it as such. Now, introducing a new proportionality constant, and we're going to refer to it as K3. Don't worry about this. This isn't going to really affect the way you solve the problems, but it just kind of gives us what our equal is going to look like, what our actual formula that we're going to use is going to look like. So we have that V. So in order to put this constant, we want to get rid of this proportionality symbol. So we get rid of the proportionality symbol, we substitute it with an equal sign, right? But we've got to have some kind of a constant. So this proportionality constant, which we multiply by K3, and what we're going to do is we want to isolate for K3 to give us the following. So K3, whatever the constant, proportionality constant happens to be, is equal to a PV divided by T. So now notice pretty much the way we've arranged our letters, PVT, right? Think about Boyle's law, right? And it's constant. Think about Charles' law, and it's constant. And think about Gay-Lussac's. Right? Notice how T was always in the denominator position with all these constants. Notice how it was P, V was also in the numerator, and notice how V is multiplied by P, and we end up getting our proportionality constant in the same order that we would combine all three of these gas laws together. So This mathematical relationship is known as the combined gas law, and you know that we can actually look at it in terms of an initial pressure, volume, temperature with respect to a final pressure, volume, temperature. So if a sample of gas is trapped at a measured set of initial conditions, the combined gas law can be rewritten as follows. Our constant is equal to Pi Vi over Ti. So we know that if we had the same, but we're looking at it as the final set, right? We've already applied these new conditions, and now it is the final state, okay? So as this gas is then subjected to changes in pressure and temperature, the final conditions of the gas can be described mathematically as the following. K3 is equal to PF VF over TF. Now, since both expressions are equal to the same proportionality constant, K3, the combined gas law can be written as follows, right, where we have our pressure and volume multiplied together divided by the temperature in Kelvin, right, but of our initial state, right, the initial state of the gas, and is equal to the same pressure, volume, temperature of our final state of our gas. So let's look at the first sample problem here. Mary Ann is having a birthday party on a mild winter's day. The weather changes and a high pressure of 103.0 kilopascal cold front, right, at minus 25 degrees Celsius rushes into town. The original air temperature was minus 2.0 degrees Celsius and the pressure was 100.8 kilopascals. What will happen to the volume of the 4.2 liter balloons that were tied to the front of the house? So take a moment, devise your plan, right, and try to figure out what are your initial pressure, volume, temperature, and your final volume, pressure, volume, temperature. Right? So pretty much, what are we trying to find? What is the question asking us for? The final volume, or VF. So try to identify your initial pressure, volume, temperature, and your final pressure and temperature. Because it's volume, the final volume is what you're trying to find. Now let's identify the various sets of units and which are initial pressure, volume, temperature, and that. So our initial pressure, 100.8 kilopascals. So it went from 100.8 kilopascals to a higher pressure of 103.0. Our initial volume of the balloons was 4.2 liters. Our initial temperature was minus 2.0 degrees Celsius. Our final pressure rose to 103.0, as I just said momentarily ago. Our final volume is what we're trying to find, so we want to find out what's going to happen to the balloons. And we know that the temperature has gone down to minus 25 degrees Celsius. So first thing, well, we know that we've got the equation as follows. So let's convert our temperature units into Kelvin. So minus 2.0 degrees Celsius becomes how many Kelvin? 271 Kelvin. Notice when we've got Kelvin units, we never have negatives. You'll always have a whole number. It'll always be positive. Negative 25 degrees Celsius will become 248 Kelvin. Okay. So we have the following. So we have units for all of them except for the final volume. So what we want to do is we want to move our final temperature to the opposite side of the equal sign. We want to move the final pressure to the opposite side. So what we're going to do is the final pressure, we're going to move it to the other side because it's in the numerator. Once we move it across the equal sign, it comes down there. Okay. Now we've got the temperature, final temperature. So we want to isolate for the VF, so we're going to move it across this side of the equal sign. So because it's in the denominator here, we are going to put it up here in the numerator. So our equation becomes, our final volume is equal to PI VI TF over PF times TI. So all we're going to do now is just substitute our numbers into each one of those letters, right? So VF equals, so what's our PI? 100.8 kilopascals. Now my advice to you guys, keep the units there, because we're going to see how we're going to cancel out the units as we work mathematically. Times 4.2 liters multiplied by 248 Kelvin divided by our final pressure, which was 100. Our final was 103.0 kilopascals multiplied by 271 Kelvin. And so just like I said, when it comes to the units, canceling out the units, so we've got kilopascal here, kilopascal here. We've got Kelvin here, Kelvin here. So we know what our units are, right? And we know we should know that even without, regardless of whether we cancel them out or not. We should know, if we're trying to find volume, which one of these units are volume. But this is kind of the fail-safe. Okay, so when we multiply all that together, our final volume, we get 3.761 liters. But as we said, what are the least number of significant digits in my question? 2. So I want the 3.7. I look at the number right after it, and the volume is 3.8 liters. So does the number, does our answer seem logical?
Yeah.
Why?
We know what 3.8 liters.
Okay, we know what 3.8 liters is. What else?
Your initial isn't far from your final.
Okay, so because we know, according to what we've learned, what's happened to the temperature?
Temperature decrease.
Has gone down, right? And we know what happens to volume. It also goes down, right? So, and did we see that with this example? Yes, because also remember, temperature went down, the volume went down. Right? So we've combined now. Notice how we've combined Boyle, Charles, Gay-lussac with the following example. Okay, let's move on to the next sample problem. An automated instrument has been developed to help drug research chemists determine the amount of nitrogen in a compound. Any compound containing carbon, nitrogen, and hydrogen is reacted with copper to oxide to produce CO2, H2O, and N2 gases. The gases are collected separately and analyzed. In an analysis of 39.8 milligrams of caffeine, using this instrument, 10.1 milliliters of nitrogen gas is produced at 23 degrees Celsius and 746 torr. Bear with me, it's a long question. What must the new temperature of the nitrogen be in degrees Celsius if the volume is increased to 12.0 milliliters and the pressure is increased to 780 torr? Of all those units, the only units that need to be converted, as your hint right now, is temperature. Temperature, we convert it to Kelvin. So read the question again, pull out what your initial pressure, volume, temperature are, and what your final pressure, volume, temperature are. Okay. And we know that what are we trying to find? The final temperature in degrees Celsius. But our answer will be in Kelvin, and then once we get the answer in Kelvin, then we will convert it into degrees Celsius. So work on that one. Let's set up just what our units. So our initial pressure, 746 torr. Our initial volume, 10.1 milliliters. Our initial temperature, is 23 degrees Celsius. Our final pressure went up to 780 torr. Our final volume went up to 12.0 milliliters. It's our final temperature is what we are trying to find. So we know, we've got the following equation. We know 23 degrees Celsius, we want to convert to Kelvin, and 23 degrees Celsius becomes 296 Kelvin. So of all these units that I need to find my final temperature. So, a couple of things that we can do. When our unknown is in the denominator, what can we do? We want to bring it to the numerator, right? That's one way. The other way is to just flip the entire equation, remember? Right? We can flip it, but we're flipping both sides, right? So we're flipping these two together, or we're flipping, not just or, we're and flipping. Well, we're doing the one side, we do the other. But now what we could do is, we could just switch these two together. But we're switching them together, so it's initial pressure and volume switches with the TF. Right? And we're just bringing the TI over. And it seems like there's a whole bunch of, I don't want to go through all the math that's involved. And in the end, this is what we're going to get. PF, VF, TI over, oh my goodness, now I'm getting lost here. PI and VI. Okay, so once we have that now, all we got to do is substitute these numbers into these letters, and our final pressure, 780 torr, multiplied by our final volume, which is 12.0 milliliters, multiplied by our initial temperature, which is 296 Kelvin, all divided by our initial pressure, which is 746 torr, multiplied by 10.1 milliliters. And so, to cancel out, milliliters cancel out, torr cancel out, and our final answer will be in Kelvin. So our final temperature works out to 367.71 Kelvin. Least number of significant digits in our question are how many? 2, right? So we take the 3.6, we look at that, so it becomes 370 Kelvin. 370 Kelvin to degrees Celsius becomes, so what does it become? 97 degrees Celsius. Your best bet though, I'm going to tell you now, is convert this answer, because it asks you in degrees Celsius, convert that answer first into your degrees Celsius with all the units, with all the digits, and then simplify your answer to your 2 significant digits. Because your question asks you, because you're technically kind of simplifying before you get to the final answer. Yeah.
If you've written out everything already in the opposite way with the numerator and the denominator, can you just indicate that you inversed it so that you get the right answer?
What do you mean? Like if you put these down here at the top?
If I put, yeah.
And then these at the bottom?
Yeah, and then if I just indicated that I inversed it.
Just make sure that when you work it out that you inverse it. The final answer kind of thing.
Yeah.
Okay?